Hi, we are Team Bombers from the University of Houston. Our project is a NASA suit user interface technologies. My name is Ngọc Nguyen.
My name is Nancy Wood.
My name is Ashwin Matthews.
And my name is Almira Shahara.
We are a team of 4 mechanical engineering students. This is our first time participating in TSGC. We've learned a lot during the past 2 months, and we are very excited to share with you about our project. The agenda will be split into 4 main parts. By the end of this presentation, you will learn about what NASA suit's tasks for this year are, how our design meet those tasks, and our plan moving forward.
In NASA suits, the primary goal of augmented reality or AR system is to assist the astronaut with EVA responsibility in a way that when they are on a lunar surface, they can use their time proficiently and in the best way possible. Navigation, geology sampling, and system states are the 3 major EVA tasks, and our goal is to design a simple and safe user interface that can help the astronaut to successfully complete their assigned missions on the lunar surface. For the navigation part of the operation, the ideal design must meet 3 major criteria. Firstly, the system must be designed in a way that can navigate the astronaut from one desired point to another. The second criteria that needs to be met is that the device has to be able to guide the astronaut back to the lander, as well as telling them how long it will take to go back. Last but not least criteria is that the design must have the ability to direct and navigate the astronaut to the areas of geological interest. For the EVA system state part of the operation, the design system must be able to interact with the suit port to execute the airlock activities such as display and control unit and umbilical interface assembly. Also, in any case of emergency, the system must notify the astronaut to return to the pressurized environment. To ensure the astronaut's safety and the success of the mission, the HMD designed by the team should inform the astronaut by displaying all the information related to the factors that I just mentioned on a screen. For the geology sampling part of the operation, the HMD system must have multiple abilities in order for the astronaut to complete their missions in the safest and quickest way possible. The HMD device must guide the astronaut through the sampling instructions, direction to how to interact and use each specific tool, navigate to the correct side, provide a unique method for taking field notes, take a picture of each sample, and finally a way to collect the samples.
So designing for augmented reality is a challenging task. Augmented reality, or AR, is very similar to virtual reality. However, in AR, components of the design will display on top of the real-world environment in our visible view. Likewise, there are some special considerations we must take to ensure that the AR experience is effective in accomplishing our desired task. The first consideration is something called interaction cost, which is defined as the sum of all mental and physical efforts used to perform a task. In this image, the user's mental efforts involve processing the GPS navigations and applying those directions to their driving, and the user's physical efforts involve operating the car and clicking through the GPS system with their hands. Generally, a lower interaction cost is desired in our UI. Now, the next consideration is something called cognitive load. Now look at the top and bottom lines of text. If I were to show you both lines and ask you to replicate them from memory, you'd probably have more success replicating the bottom line. This is because the brain processes information in separate chunks. You might notice the bottom line features easily recognizable acronyms like IBM or USA. The brain therefore processes each acronym as a single chunk of information, resulting in a total of 4 chunks. The top line, however, features randomly placed letters of differing lengths. This forces your brain to treat each letter as a separate chunk, resulting in a total of 12 chunks. Cognitive load theory tells us that the brain can only handle so many chunks of information at once, and the lower that amount, the better. Now, our last consideration is seamless task switching. Whenever you operate your smartphone, you're very easily able to switch applications or tasks through the app browser. Similarly, we want our AR system to exhibit the same qualities when switching from an operation such as navigation to another such as geology sampling. Overall, we want to keep these three theories in mind when designing our AR UI.
In order to design the user interface for the HoloLens 2, we first ideated and brainstormed ideas on how to tackle the goals given by the NASA Suits Design Challenge. Then a user flow map was created to show the overall flow of our user interface design. Lastly, low-fidelity wireframes or prototypes of screens were created in order to test the user interface design. In the next few slides, we'll go into detail about our design for each task.
Here's the AR display during navigation operation. The astronaut will be able to see the destination indicator, which shows the location that they are heading to. Right below that, there will be a descent and ETA timer, showing them how long and how far it would take them to get there. Now, my favorite is the directional hologram, which shows the path where the astronaut can follow to their destination. Those holograms are designed in a way that they are clearly showing the map, but at the same time not too overwhelming so that the astronaut can still see any obstacle on their way. The holograms would follow the shortest route provided by available data, and they will also act as assistant for any elevation changes. And lastly, we have the collapsible map. In this view, the astronaut will be able to see not only where they're heading to, but also any geology sampling sites and points of interest. The orange path here shows the route overview. It's very similar to the GPS navigation system on Earth. And most importantly, we have buttons for astronauts to switch destination or cancel their current route.
When the astronaut is ready to start completing their geology sampling missions, they can go to the geology sampling menu as shown in the image. The geology sampling menu will have the option to either go through a few geology sampling tutorials or to choose a geology sampling mission to complete. Once the astronaut wants to start their geology sampling, they can click on the missions button to fill out a field note to take down their observations. The field note will be able to save qualitative information as well as pictures of the geology sample. The qualitative information such as color can be noted by selecting a choice from a drop-down menu. This will be done by just tapping the desired selection in the drop-down menu. The pictures can also be taken and saved on the field note by tapping the Take Picture button as shown in the image. Also, the astronaut can retake pictures as needed. When the astronaut is done taking the field note, they can tap the Save Note button, which will save their field note.
Now, in the emergency state, the astronaut must easily be able to return to a nominal condition or return to the lunar lander. If the astronaut experiences an anomaly, a screen displaying a warning indicator, anomaly description, along with the tool used to fix the anomaly should appear, if applicable. In the overall design, we attempt to display the key components of the in a non-intrusive manner. To do so, we create a menu that only appears when the astronaut stands still. Now, when this occurs, the full system indicators will appear at the top of the screen. Additionally, the astronaut can access the navigation and geology sampling menus at the bottom corners of the screen.
In order to implement our design into the HoloLens in a timely manner, we've created a project plan which we'll talk about in a few slides. The major accomplishments that we have completed and submitted so far are our suits proposal and TSGC midterm report. The TSGC poster that has already been submitted and today's presentation will wrap up our completed milestones. Moving forward, we're planning to submit our final report to TSGC by December 4th. We will have 4 total outreach activities, and those will be held sometimes in months of February, March, and April. Our plan is to have our UI built in HoloLens by February 26th, followed by testing AR usability on March 1st. Also, the human-in-the-loop testing will be held on March 26th, and finally, our final system will be delivered to NASA Suits on April 16th.
And that concludes our presentations. Thank you for listening, and we hope to see you later today at our team meet and greet.